Hello everyone, my name is Yuan from Technical University Berlin. It is my pleasure to share my experiments in Object CXR challenge today. First of all, thanks to Phone Healthcare providing such nice dataset. First, let's take a look at the overview of the dataset. We have 10,000 X-ray images, which was front up-body X-ray, and they are split to train, validation, and test evenly, and in each that split we got 50% with objects, 50% without any objects, and furthermore, in the training set, images with objects, most of them are single object. It means half of them, that's 20%, 25% of images has only one object. The number of objects plot in this picture. The annotation we got, that not standard annotation as object detection or segmentation, and there are different types. Most common one is the bounding box, and also there are arbitrary polygons, and this nature of annotations, the competition have chosen also the matrix by two. One is the classification. The most important thing in X-ray falling object detection scenario is we want to know if there is any falling objects within the image. The next thing is localization. We want the model can detect where the falling object is, so that the doctor or human can quickly review the results of the detection. The organization have chosen both well-thought metrics. For classification, we are going to have area under the curve, and for localization, we are going to use frog. Both have well balanced between the accuracy and the recall and the false positives. As a result, this challenge presents some unique challenges compared to other object detection problem. First is real or unseen objects. It is already stated in the challenge page that our objects can be rarely seen or never seen in the training set, and that is our target to detect any falling objects presented in the test set. The next challenge is annotation type. As we seen in the last slides, there are not standard annotation for object detection or segmentation, and this means we cannot directly use the existing framework or object detection framework for this challenge. And there's already organizer provided the baseline using object detection directly, but that's not optimal. Last but not least is our training objective. According to our metric, the classification is the most important objective, but our localization are also very important as well. The challenge is we have multi objectives which are not standard from existing object detection framework. My solution is that first use bounding box object detection as the baseline, then use the existing technology to tackle the challenges presented. I would highlight 4 parts in my solution. They are data augmentation and finding the center of objects, and fuse the classification, and finally use test argumentation and ensembling to boost the performance. I started to use bounding box object detection as the baseline, since there are so many object detection framework out of there. I have tried different frameworks, started from fast RCN, cascaded RCN, and also single object detection frameworks like ReturnNet and efficient detect. In the end, I decided to use efficient detect, and because all the framework I tried have reached equally good results out of box, and efficient detect have its own advantages as the recent state-of-art single stage object detection. The model itself is very small and efficient. Second, it uses neural architecture search, which results well balanced between performance and the speed and the accuracy, which also we have results from small network to bigger network. Pre-trained weights are available, so that I can experiment different size of the network on the size of the dataset we have. Furthermore, I have re-implemented the efficient net detector in PyTorch myself, so I'm familiar with the code that I can further improve the model architecture. Here is the basic setup of my baseline. After a few testing, I found that efficient D3, which is the middle size of the model, that performs best. When it is better performed in accuracy than D2, and D4 performs similar well, but it's bigger than the D3, so it takes longer time to train. For all the experiments, I will use the same setup. All the models are use COCO pre-trained weights with mixed precision training. The optimizer were SGD with momentum, and the learning rate was scheduled by cosine annealing with warm-up. All the models are trained 40 epochs, and that's enough for model to converge. My baseline with the efficient detector D3 could reach very similar performance as the provided fast assay baseline. The OG is about 0.921. Next is try to tackle our challenges presented. The first one is detect unseen objects, which directly affect the generalization of our model, which I think the data augmentation in this case would help. While data augmentation is quite common and powerful technology for generalizing our models, in this challenge I have used a big range of different data augmentations. They have been proved in the past research. Some basics like the size flips and color changes, they help. And furthermore, the cutout and the distortion helps a lot in this dataset, as well as the auto-augmentation policy learned in COCO dataset, which further improves the performance. On the right side, there are a few examples showing that the augmented results after a few experiments without too much tuning, the network performance improved about 2% in OG and also more than 2% in frog. Then I looked into our annotation challenge again, which is at the moment we just use the label, create the bounding box, and take it as it is for our object detection framework. Unfortunately, this presents a problem that many of our annotations are polygons, which the simple bounding box without our center of the bounding box is out of the annotations as shown in this picture. That will result first bad frog performance, because our detected bounding box will be center will be outside of the annotation, and the fork is calculated by the coordinates lies within the annotation or not. So then I use an algorithm called polylabel, which finds the inaccessibility pool that is most distance far away from all the polygon outlines. As shown in the right side, the new bounding box recenter itself to make sure that the center will be within the annotation, and this center is also far away from the outlines. The polylabel algorithm itself using quadrat tree to search these optimum points. I have to pre-calculate all the new bounding box beforehand. So then, with this reallocated the bounding box, the model performance could improve further. Not really much, but about 0.2% in awk and 0.5% in frog. I was expecting it to improve more, while in the object detection framework, the center is very important in our ankles, correspond to our ankles, because for example, the detection results around this bounding box center will have perspective view mostly focused on this area. So it means if our features are of the objects are not around this center, they are not really optimized for detecting such objects. Therefore, I believed the centralized objects would help in this detection as well. Then the next thing is I focused on our metrics, which is the fact classification is our first and most important metric. That is awk, while our object detection framework predicts a list of objects, and we took the most possible objects as our results for the whole image. This I think we can improve by giving image level classification as the training objective. First, I introduced a new branch which uses the image level as a optimization target, which takes the highest level output of the backbone, and then through the max pooling and drop out and linear layer, which are quite common components used in image classification. While this helps the classification by indirectly giving the overall classification results. Furthermore, I directly fuse the overall classification branch to our object detection output. By fusion, I mean I try different combination. the fusion combines the two outputs of these two branches. I tried two different combinations. One way is I use the sigmoid output of this branch, multiply the output of the original bounding box score, or use resonator-like structure directly plus this output together. Both methods result very similar performance in the end. With this architecture modification by introducing classification laws and fuse the classification branch to the bounding box branch, the model could improve the validation score more than 1%. However, the frog score had decreased a little. That's, I think, due to the fact that I just added the classification loss directly to the overall loss, which means the classification takes more weight in the overall loss that also results the localization or bounding box loss have less weight as it reflects in the final localization score decrease a little. But in our competition, we take most care about of the classification, so I haven't tuned anything about this. And then I made my submission to the against the test set. It was a little surprise that the test set have exactly the same results as the validation set. While this is a single model and single pass inference results really good, and I tried to use test augmentation and ensemble technology to further improve the score for the competition. In my final submission, I have used 3 different trained models. The first model is the EfficientNet D3, which gives my best local validation score. And the second model is a slightly bigger model, Detector D4, and it has a slightly worse score. And the third one is the same architecture as the first one, but I trained it with a different train and validation split, which means I put the validation dataset in the training and took the same amount of images from training as the validation. So the score, the local validation score, can't directly compare here, but I think it will improve the variety of between models that also will improve the overall performance of the ensembling. And for each of this model, the test augmentation was used in the inference. Overall, there are 4 passes have been used in the inference: the original image and the horizontal flipped image, and also scaled up 1.2 and 1.4 times to the compared to the trained image size. And finally, there are 12 submissions assembled together by a modified version of Nomax separations, which not only doing the separation but also do average of the merged bounding box and the center. The standard NMS will just suppress the low scores that only takes the highest score and its bounding box. Here I do average all of the matched bounding boxes and also average the center, which give me comparable slightly better performance. And the final score in the leaderboard was 0.963, and also a really good result in frog, as this timeline shows the progress of my solution from baseline model to my basic score. There are still things left for further future work to improve. First, I think from the experiments, the data augmentation have improved the score a lot, but it could be further improved by auto-augmentation experiment that is searching different combination of the data augmentation, and also synthetic data would help to detect more unseen or rare objects. The second part is can be included is using the annotations, the way that we can fit the human annotation as the segmentation to our training objective. Last but not least, the classification branch in my solution is rather simple and direct. More complex architecture or modification could be applied with attention or context network. I plan to make an open source in the GitHub. If you have any question, you can raise the issue there. Thank you for your attention.